Does anybody need a copy of those? This is the last set of lectures. There's lecture notes 21, which is on the web, but we're not going to go through it. So I'll mention something about that. It's the multi-input, multi-output case for feedback control, and I'll show you how it's done, but we won't go in detail through the algorithm. So what we cover in class is what you're responsible for the homeworks and for the final exam. So let's just talk about a little bit of the roadmap for the rest of the semester. So this week we're going to focus on controller design, lecture notes 20, and observer design, lecture notes 22. So doing that today and Thursday. Thursday, for the first 15 minutes of the class, will be the course evaluations. All right, so they'll come in. It's all done online now, and what I think the university is finding is that there's a lower hit rate. Not as many people respond as when we used to do them on paper. So that's why they come at the beginning of the class instead of the end of the class, so people will actually stay and fill out the. So you can bring your device and log in and fill out the course evaluation on Thursday, or you can do it in your own time. It doesn't really matter, but it is great for us to get your feedback on it. In terms of the rest of the semester, so Sylvia, I don't think you've announced this yet, right? But in terms of there's the last section is actually this Friday afternoon. So last section is this Friday as normal. And then did you decide, Sylvia, on a time?
Yeah, so on Monday we're going to do a final review. I'm thinking of doing a similar thing as what we did with the midterm review, except starting it at 12:30. And going through to 2:30, and then I had my office hours 2:30 to 3:30. This is because I am going to a conference the next day, so I won't have my office hours on Wednesday.
Okay.
But I'll send out an email about this.
Okay. So
if you're not getting emails, please let me know. Occasionally I get somebody who contacts me telling me they get no emails. So please let me know if you're not getting them.
All right, so, and then I'll hold office hours. To complement that, I'll hold office hours next week, probably towards the latter part of next week. And I'll send out an email about that. Good, okay, so let's get back into this controllability, observability, which we ended last day's class talking about the linear time invariant case of controllability, and we started going through the proofs. And I said the observability proofs are exactly the same as the controllability proofs, and I gave you, as you see on homework 8, one of your homework problems is to actually go through those proofs for the observability case. Okay, so you can go through those and show the, basically the two key important theorems there are the rank n of the controllability matrix or the observability matrix. All right, so we defined as either Q or C the controllability matrix, which is a short fat matrix, A to the n minus 1b. So it's made up of columns, B, A, B, up to A to the n minus 1b. And likewise, the observability matrix is constructed from rows C, CA, CA squared, up to CA to the n minus 1. Okay, so for controllability, we require this matrix that has n rows and n times ni columns. That has to have rank n. And for observability, this tall, thin matrix, which has n columns and n times n out rows, that has to have rank n. And then equivalently, we have the PBH, the Popov-Belovich-Hautas test, which is the rank of the following matrix, which is Si minus A B, has to be n for all S in the spectrum of A. And likewise, we have the observability test, which is the rank of Si minus A, and then we stack it with, in terms of rows, with the C matrix, has to be n for all S in the spectrum. Okay, so those are our tests, and they're typically easy to compute tests, and so you understand the equivalence So the theorems that you have to prove for observability in the homework are really understanding the equivalence between the observability Gramian that we developed and proved for linear time varying systems, and thus it holds for linear time invariant systems, and these simpler tests for testing the rank of these matrices. Okay, so these are simpler than looking at the Gramians, looking at the rank of the Gramians for, or the corresponding Gramians for linear time invariant systems. So there's a nice fairly straightforward result that comes out of this, and so this is controllability, this is observability, but we have two kind of weaker notions of controllability and observability. One is called stabilizability, and one is called detectability. So a system may not be controllable, but it may be stabilizable. Okay, so what is the test for stabilizable? It's written in terms of the PBH test. So the rank of Si minus AB should be equal to n. And now we look at not all eigenvalues of A, but for all eigenvalues of A, for all S eigenvalues of A, which are unstable. All right, so we write that as for all S in the spectrum of A, but not all spectrum of A, just those that intersect the right half plane. Okay, so these are all unstable eigenvalues. All unstable eigenvalues. And the idea is that we don't need to be able to control the location of all the eigenvalues of A. If they're already in the left half plane, or the open left half plane, we could just leave them where they are. What we really care about for stabilizability is to be able to control the unstable eigenvalues. So the ones that are on the j omega axis and the ones that are in the right half plane. All right, so this is the closed right half. And similarly, we have a weaker notion of observability, which is called detectability. And you can imagine now what that is. So now the rank of Si minus A stacked with C should be equal to n for all eigenvalues of A, which are also in the closed right half plane. So if we can't observe a stable eigenvalue, we don't really worry. It's just gonna cause the system to it'll be some mode of the system which will just decay exponentially. It'll be fine. What we really care about is being able to observe those eigenvalues, so to see at the output those eigenvalues which are unstable. All right, so often this is what we care about. We don't really need to be able to control or observe modes which are already in the left half plane.
You said modes.
So what's a mode? Yeah. And now I'm asking you, what is a mode?
I don't know, we just talked about modal before.
Yeah, we talked about hidden modes, right? When we talked about eigenvalues that you can't see at the output or you can't control from the input. So remember we use this term mode and eigenvalue interchangeably. Okay, so let's move on to talk about controller design. And this is really a nice sort of set of topics to end the course on, because it's fairly intuitive. It uses the theory that we've built up over the course, and it's kind of satisfying. It's sort of, I always call it a little bit therapeutic after all of the theory that we've been developing in the course, to actually use it in a very intuitive way and kind of a very satisfying way. So let's start with controller design. And I'm going to actually go a little bit ahead and then come back. And so I'm going to start, if we're following along in the lecture notes, this is lecture notes 20, page 7. Let's just come up sort of with an intuitive idea, or the key idea of control design using state feedback. And let's do it via an example. Let's be very concrete to begin with. So it's a linear time invariant system here. X dot equals AX plus BU. And the idea is, how do we, or can we choose an input u, which when we plug that into the system here, we're able to have a closed loop system which has closed loop eigenvalues anywhere in the complex plane. I mean, typically you'd want them to be stable, but let's be general now, and let's ask, when can we use an input u to place the eigenvalues, once you've plugged that input in, of the closed loop system anywhere in the complex plane? We're going to be a little more specific, motivated by some earlier work that we did in LQR, where we looked at state feedback, and then also motivated by our more recent lectures on state feedback and the preservation of controllability under state feedback. We're going to ask the following question. Consider, so we're not just going to consider any old input, we're going to consider some state feedback. So we use minus, u equals minus f, where f is a matrix, times the state x, and let's just put some, what do we call it, v, some auxiliary input, some new input into the system, v. Okay, so this looks familiar from what we've done before. And the question is, when can, or under what conditions can we choose f, the matrix F, because in general we know that u and x are vectors, to place the resulting closed loop eigenvalues, or modes, anywhere in the complex plane. Okay, so if under this topology of the control. And we'll actually now we'll, so that's our general question. Now we'll look at this through an example. And I chose the example where a is -1, some parameter little a, 3, -2, and b is so it's a single input system. There's only one input, and the B matrix is 0, 1. Right, so what does state feedback look like? So we've got our system here. It's got state x, feed in an input u. We're measuring the state directly. All right, so we're assuming we can measure the state directly. I haven't even written an output equation there. So we're assuming we can measure x. And we're going to feed that back through a gain, f. Negative feedback, and we'll put our auxiliary input there. So u is equal to v minus fx. Okay, and so the closed loop system, we've already done that calculation. We know what the closed loop dynamics look like. Let's be very specific and write our matrix F. So it's a single input system. There's two states. So F is going to have two components. I'm just going to call them F1 and F2. And we get to determine F1 and F2. Okay, so the closed loop system is just going to be, let's repeat this calculation so we remind ourselves of that. AX plus BU is the open loop system, but U is equal to minus FX plus B. All right, so we'll plug that in, and then we get that X dot is equal to A minus BF X plus B. That's our new closed loop system. Closed. So the real question now is, how can we use F1 and F2 to place the eigenvalues of A minus BF anywhere we want in the complex plane? So for this example, let's just work that out. So what is A minus BF? 3 minus 2 minus 0, 1, F1, F2. And we see that, let's write it down here. We see that A minus BF is going to be minus 1, A, 3 minus F1, and minus 2 minus F2. All right, so we can write down the characteristic equation of that matrix. It's going to be a function of F1 and F2. And we get that the characteristic equation of the closed loop system, I'll use lambda instead of S like I do in the notes. So the characteristic equation, let's use our notation here, chi hat A minus BF of lambda is the characteristic equation of the closed loop system. And if you work it out, it's lambda squared plus lambda times F2 plus 3. I've factored it out, or I've written it in terms of decreasing powers of lambda is what I should say, plus 2 plus F2 plus A times F1 minus 3. Remember, A was a parameter in my original matrix, and F1 and F2 are just the parameters of my controller, my feedback controller. Okay, so that's my actual characteristic polynomial. I'm going to write actual to remind ourselves. This is what we have. This is the actual characteristic polynomial of the closed loop system of A minus B. This is what we have. All right, now I'm going to look at a subset of this question. Instead of asking, can I put them anywhere in the complex plane, I'm going to ask, can I place them at some desired values that I choose? All right, so I'm going to ask now, can I place those closed loop eigenvalues using F1 and F2? Can I place them at some, desired location that I came up with? And in this example, my desired location is, I want the closed loop eigenvalues at -2 and -3. So this is my desired closed loop eigenvalues. Okay, so from that I can get what the desired characteristic polynomial is. So desired characteristic polynomial is just going to be lambda plus 2, lambda plus 3. That will give me roots at -2 and -3. The desired characteristic equation, just set that to 0. And so writing that out in terms of decreasing powers of lambda, again, that's lambda squared plus 5 lambda plus 6. Okay, so I have my actual characteristic polynomial and I have my desired characteristic polynomial. So what do? Match them, right? That's why it's therapeutic. You just have to match the coefficients of the polynomials. So this gives F2 plus 3 is 5. Match them. Match coefficients of desired and actual. So F2 plus 3 is equal to 5. And 2 plus F2 plus A times F1 minus 3 is equal to 6. Okay, so you end up with a solution which is F2 is equal to 2 and F1 is equal to 2 over A plus 3, which is obviously only valid if A is not equal to 0. So yeah, I mean, we can choose F1 and F2, and that's really just the algorithm. And that's the basics of all this pole placement. Pole placement is a sort of older term that's used. We should call it really eigenvalue placement, because we're measuring the state, we're feeding it back through a state feedback matrix, and we're using that to try to adjust the eigenvalues of the new closed loop system to be in a desired location. Okay, so that's fairly satisfying, but what happens when A is equal to 0? So when A equals 0, it becomes a problem. We can no longer place those eigenvalues anywhere we want. And if we look over here to kind of explain that, when A equals 0, you see the dependence of the actual characteristic polynomial on F1 drops out, and you end up with an actual characteristic polynomial. So when A is equal to 0, the actual characteristic polynomial, so chi hat of A minus BF, is just dependent on F1. And if you factor it, so drop the dependency on A and factor that polynomial, you can see kind of immediately what happens. So the eigenvalue, in the open loop case, the eigenvalue that was at -2 can be moved by F2, but the eigenvalue that was at -1 can't be affected. It's just going to stay there. So F2 comes in and it affects directly the location of the eigenvalue that was at -2 in the open loop system. Does everybody see that? Okay, so the eigenvalue, or the mode, so eigenvalue equivalently mode at -1 cannot be affected by state feedback. What do you think the rank of our controllability matrix would be in this example when A is equal to 0? 1. Good. So if we check that, so I'm going to check the controllability matrix, which is just B, A, B. So it's 0, 1. And I'm going to set when, I'm going to consider this case when A is equal to 0. So then AB is just negative, is just 0. So you see there's a problem there. And over here I get -2. Okay, so the rank of C is equal to 1. So in fact, we can say a little bit more. The rank of the controllability matrix, when it loses rank, that indicates a loss of controllability. And we see it directly in this example. Full rank would have been 2. When A is equal to 0, the rank of the controllability matrix is 1. And you can see that loss of controllability and the loss of ability to control, to move, to shift that eigenvalue, which was at -1 for the open loop system, it's got to stay at -1 now. State feedback isn't going to shift that eigenvalue. So the rank of the controllability matrix tells you about the rank of the subspace of n, of Rn, that you're able to actually control. Okay, so we can dive from this motivational example into the more general result. And the more general result is stated through 2 propositions, or I've stated in the notes as 1 proposition and 1 theorem. And they're stated as follows. So now I'm going back to page 3. So we're jumping back from that example to page 3 of the lecture notes, 20. And this is a proposition, which is basically it's the controllability and eigenvalue placement proposition. And it's stated here for single input systems. For single input, we don't even have an output, so we'll just say single input systems. And that proposition goes as follows. So suppose you have a system, a time invariant, so for single input, let's put that in because that's important. LTI systems. Okay, so suppose you've got your system x dot equals ax plus bu. Then the ability to control this system, or to completely control this system, is related to the ability to choose a feedback gain matrix F, which multiplied by the state, so assuming that you're measuring the state and you feed that back, to place the eigenvalues of the closed loop system anywhere in the complex plane. So kind of just now generalizing the example that we've just done. And we state that general result in 2 stages. We state it through a ability to transform the system to what's called a controllable canonical form. Okay, so the proposition goes as follows. So we consider this system. There exists, so this is one side of the proposition. There exists an n by n matrix T, so this is a matrix T which is non-singular, and T inverse exists, such that when the system AB is transformed through a similarity transform based on T, so I'm going to take these two matrices and perform a similarity transform on A, and that gets me to the following form, which is called the controllable canonical form. It's a matrix where the first n rows are all zeros except the superdiagonal, which is 1, and then the bottom row has generally not equal to 0 coefficients, minus alpha n, minus alpha n, minus 1. Those coefficients are very important. I'll come back to them in a minute. Let's just look at B for a second. And T inverse B is a matrix, or a vector, whose first n minus 1 entries are 0 and the last entry is a 1. Okay, so you're given a general system, general LTI system, single input, single output. The proposition states that there exists a similarity transform T, which takes AB to this form here. So that's one half of the statement. If and only if the system AB is controllable. Or as we defined last day, controllable, completely controllable. We use those synonymously. All right, so we can do either rank test we want for the controllability test. But if you're given a system AB which is controllable, then you can prove that there exists a transformation which takes the system to this form here, and that form is called controllable canonical form. Controllable canonical form. We've already seen a few canonical forms already. We've seen diagonal form, we've seen Jordan form. But this is a form where it involves both A and B. All right, that similarity transform T inverse, transforms A to this particular form here, and it transforms B to this particular form here. All right, so in terms of what we've been looking at in terms of canonical forms, this is really the third one, but it's the first one that involves B as well. Question?
Is that a single one, or do you have multiple?
There is for multiple inputs, there is also a controllable canonical
I think
form.
basically this transform sort of puts all the controls onto one ratio between each one, and you can sort of dial one dial, all of them up, all of them down. But you could have more than a single dimension for that.
Yeah, but in this case, when it's a single input system, there's only one T which takes, if it exists, there's only one of them, which takes it to this form in particular. So these coefficients are actually special coefficients. If you work out the characteristic polynomial of a matrix in this form, you find that the coefficients of the characteristic polynomial are just these alphas, which are on the bottom row. That's an important remark. We'll come back to it, but let me put that up as a remark right now, because I like that. It means that you don't have to go ahead and compute the characteristic polynomial once an A matrix is in controllable canonical form. You can just write it down by reading off the bottom row. So it's very specific to that. There's only one transformation that takes you to that one form. So the characteristic polynomial, I'm going to write this as a remark. We'll come back to the characteristic polynomial, the car poly of, and I'm just going to use the notation over there. So we put A into controllable canonical form is the following, s squared plus, and now you have to read backwards. So s squared plus, even though that's minus alpha 1, this is plus alpha 1 s, not s squared, s to the n. Sorry, I'm thinking about our two-dimensional example. Alpha 1 s to the n minus 1 plus alpha 2 s to the n minus 2 plus plus, and then the last one is alpha n s to the 0 is equal to 0. So that's the characteristic equation. All right, so once you've got a matrix in controllable canonical form, you can just write down what the characteristic polynomial is. And you can check that. Just go ahead and check that. It's easy to check. Okay, so that's one part of the proposition. And then the second part, and we've proven it in the notes. I don't think we're going to go through the proof in class, because I gave you a problem. I actually sort of wanted you to go through the calculation of a controller design of a system that's in controllable canonical form. So for those of you who've got to problem 5, I think, of homework 8, you'll see that you actually have to work this out. So I don't think it's really, proving it is nice, but it's a little bit fussy. And I think it's more interesting just to do examples of it. But you can go through the proof if you want. So that's the first part of the whole, the first part of this stage of relating controllability to the ability to place eigenvalues via state feedback. So we've first of all got this sort of intermediate step. If you have a controllable system, then you can transform it to controllable canonical form. Now the second proposition, or theorem as I have in the notes, is if you have it in controllable canonical form, then you can place the eigenvalues anywhere you want via state feedback. And that's what you have to do in problem 5 of the homework. All right, so this is the theorem on page 5 of lecture notes 20, which says that well, it's actually, this theorem says the whole thing. So let's actually write the theorem that we have on page 5. It says that if AB is completely controllable, and let's phrase this properly. Suppose AB is completely controllable, and and we use this, this is the way we basically say formally that we can place the eigenvalues anywhere we want. Let's define some polynomial whose highest order coefficient is 1. So we call that a monic polynomial, which is s to the n plus pi 1 s to the n minus 1 plus pi 2 s to the n minus 2 plus pi n s to the 0. Be any monic polynomial of degree n with real coefficients, so these pi i's are real numbers. Then there exists a matrix F. Okay, so that matrix F is it's a matrix. It's a single input system, so it's just a 1 by n dimensional matrix. So F transpose is an Rn, such that the characteristic polynomial of A minus BF is equal to that any monic polynomial you can choose. So this is an equivalent way. This is an equivalent way of stating that if AB is completely controllable, CC means completely controllable, then there exists a matrix F such that the eigenvalues of A minus BF can be placed anywhere in the complex plane. Right, so there's sort of there's n degrees of freedom here. We can either write them as the n eigenvalues of A minus BF, or we can write them as the n coefficients of the characteristic polynomial. And so we've just stated it in the first part of the theorem. We've stated it by saying, choose any characteristic polynomial. Then if the system is completely controllable, you can find a feedback gain matrix such that the characteristic polynomial of your actual closed loop system, A minus BF, is that monic polynomial that you've chosen. But that's equivalent to saying, because there's n roots of this, it's equivalent to saying that if the system's completely controllable, then you can choose a feedback gain matrix that puts the eigenvalues of the closed loop system anywhere in the complex plane.
Why do the nodes have A plus BF?
Yeah, it doesn't matter. I think there's a little bit of a disconnect because I was using A minus BF for this example, and the theorem's written in terms of A plus BF. Probably because I used the notes from Kelly and Sower. But as we know, if it's you know, A minus BF and A plus BF are really the same thing because I could just absorb those negative signs in the matrix F. Okay, so the way the proof goes of this theorem is basically first, if the system is completely controllable, we know we can transform it to controllable canonical form. And then once the system is in controllable canonical form, you can see very easily, I mean, maybe you can see directly now by the structure of A and B, but once you take that, the new B, the T inverse B, and you apply you apply that in closed loop, so you have A minus BF, and you look algebraically at that, what that BF does is it just affects the bottom row of this matrix here. So it just affects the coefficients of that characteristic polynomial. And that's what you've seen if you've already done problem 5 of the homework, where I ask you to just do this explicitly. Okay, so a system being completely controllable is synonymous to saying that there exists a feedback gain matrix, which, such that when you apply that and you get A minus BF as your closed loop system, the eigenvalues of A minus BF can be anywhere. All right, so then we can, start to use this as a tool. We can start to test about, if a system is controllable, if a system is controllable, then we can basically place those eigenvalues anywhere we want. So we can place them in desired locations. Typically you want them to be stable, so you'll choose your desired characteristic polynomial such that its roots are all in the open left half plane. Question?
Is F a unique one, or are there different Fs?
It is for a single input case. For a multi-input case. So this, and that's the topic, I didn't print them out, but lecture notes 21 goes into the multi-input case. It's exactly the same algorithm for the multi-input case. It doesn't matter that F is, it doesn't matter if B has 1 column or 2 columns or 3 columns. You're still using the fact that if that multi-input system is completely controllable, then A minus BF, where F is now, it's more than just a row, it has multiple rows to it, you can place the eigenvalues anywhere you want. And when it's a multi-input system, you have more degrees of freedom in that F matrix than you need, typically. It depends the sparsity of the B matrix and everything like that. But then you have some choice. And then there's different algorithms about how you choose that. And in lecture notes 21, you can take a look and see that it's basically, there's one algorithm for doing that. Question?
Will you ever be interested in shaping the closed loop dynamics into something that's Berkeley blocks?
That's a good question. So the question is, would you be interested in choosing your feedback matrix F so that A minus BF is already in some kind of canonical nice form, like a Jordan block form? I don't think so. Or diagonal?
I mean, if you're making the closed loop dynamics non-diagonalizable, so there's a polynomial coming back.
Let me think about that. No, that's a good question. First of all, it doesn't matter if it's diagonalizable or in Jordan form, because if it isn't, you can always transform it. But your question is deeper than that. Your question, I think, what you're asking is, can you choose that can you choose your F matrix so that you can make the system, you can, make it diagonalizable when it wasn't before, or in?
No, I was asking whether you would ever want to make the resulting A plus BF not diagonalizable, but still stable.
There are probably cases when you'd want to do that. That's not a problem I've really thought about. Yeah, let me think about that, because I think that's an interesting question. What you typically want to do is you want to choose F to place the eigenvalues in locations that are, okay, well let me ask you, what would you typically want to do? You're given an open loop system, it's got a couple of unstable eigenvalues, it's got a bunch of stable eigenvalues. What do you think you would do in general? I mean, this is a very generic question because it really depends on the system at hand, but how would you choose F? What are some considerations you would put in for choosing F? I mean, choosing F such that you're trying to, let's talk about what you would try to do to those eigenvalues from the open loop case, where you've got some unstable and some already stable, to the closed loop case. What would you want to be able to do with F?
Just stabilize it.
Stabilize it. Okay, so you'd want to move the eigenvalues that are unstable over to the left half plane.
Yeah.
All right, so you want it to be stabilizable. Even if it's completely controllable, would you necessarily, when would you want to, say, shift the eigenvalues that are already stable? Like this example we had that motivated this. I had a stable eigenvalue. I couldn't move it, but it was already stable. So when would you want to move that?
Maybe move it far away from the origin.
Faster, right? I think you're both saying the same thing. So shift it further away from the j omega axis so it becomes faster. Yeah, my point is, typically if you need to, but often, what control designers do is that if that eigenvalue is already stable and you're okay with the speed of response, they typically don't move it too much. Because what would moving it require in your feedback matrix F? Controllability, but yeah, control effort. So it means you would have to, basically, let's choose an F here. So the components of F, if you're going to try to move every single eigenvalue, you're going to need, F is going to have to provide action on all of those eigenvalues. So it typically means you get a bigger matrix F in your feedback path. And what does bigger gain in your feedback path result in? Large control input, perhaps amplification of any noise that you might have. So sensor noise, I mean, we're measuring state here, but measuring that state, that noise gets amplified by F. So typically you try to do the least amount that you need to do to be able to get the system to do what you want it to do, so that you don't have like large gains in your feedback loop. We'll come back to that point in, as we'll revisit that point when we talk about observer design as well. Question?
So do you actually have a way to kind of like finely tune your transient response? Because like with frequency domain methods, you can like control the placement of your zeros, so you can get like a certain transient response. Is there any way to do that here?
Here, so in frequency domain, you can do these kinds of loop shaping ideas, which tunes that more closely. You could do the same thing here. We haven't spent a lot of time talking about zeros, but that's really the, you can take a look at the overall effect of placing, what that feedback matrix F is doing to the overall transfer function of your system, and then look at the response. So what you can do in frequency domain, you can also do in the time domain here. And the algorithm that I showed you, we're not going to go through it in class, but in lecture notes 21, the multi-input, multi-output algorithm is just one example of, when you have more degrees of freedom in F than you need, how you might use that for design. Okay, so we have some theory here. Let's do some examples just to illustrate this theory. And these examples, I'm sort of skipping back to page 16 of the notes. All right, so we've got this nice result now, which relates complete controllability of the system, which is a testable it's easily testable for LTI, and it's sort of somewhat easily testable for time-varying systems. To the ability to choose a feedback gain matrix to place the eigenvalues anywhere you want. Okay, so here's an example. And in the notes, I actually did this example 2 different ways. So here, again, LTI, single input, single output system. A is -1, 0, 0, -3, so it's already in diagonal form. B is 1, 1. All right, so when you look at that, you think, aha, that must be controllable because of what B looks like. Let's just check. So if you check, the controllability matrix is, so this is page 16 of the lecture notes 20. The controllability matrix is BAB, so that's -1, -3. So you see that the rank of C is equal to 2. Therefore, the system is controllable. It's completely controllable. Both of those open loop eigenvalues at -1, -3 can be moved by state feedback. Okay, so we want to actually, for some reason, we want to shift them from where they were, so they're at -1, -3, and we'd like to put them both at -2. So this is a little bit of a textbook example. It's not really clear why you want them to be there, but the fact is you can, since the system is completely controllable, you can design a feedback gain matrix to place it. So as I said in the notes, I solved this problem 2 different ways, kind of following the proof of the theorem, or this kind of problem that you have to follow in problem 5 of homework 8. I first transformed the system to controllable canonical form. And then once it's in controllable canonical form, it's just really almost by inspection how you design that matrix F. And then I transformed it back. So that's sort of 3 pages if you follow the notes. Often when the system is small, you don't do that. And most of the time, I don't typically transform the system to controllable canonical form. It's more of a vehicle for proving the ability to place the eigenvalues anywhere you want than something that you would typically use computationally. I think the algorithms in MATLAB use this because they're doing it for general large matrices. So they want a canonical form to be able to transform to, so they can always use the same canonical algorithm for pole placement or eigenvalue placement. But typically for small systems, we would just do it directly, kind of like we did that first motivating example. So it's a single input, single output system, so we're just going to let F be like we had in that example, F1, F2. We compute the actual characteristic polynomial of the closed loop system, so A minus BF. First, let's write out what that matrix is. -1. So I'm just writing it out, but you can go through these examples, and you'll have some opportunities in the homework to do a couple of these problems yourself. But as I say, it's kind of almost therapeutic because you're computing, the characteristic polynomial of A minus BF. So the actual characteristic polynomial is S squared plus F1 plus F2 plus 4S plus 3 plus F2 plus 3F1. And the desired characteristic polynomial, what's the desired characteristic polynomial? We want both of the closed loop eigenvalues at -2, so that gives us a desired characteristic polynomial of
1 plus 2 squared.
S,
Yes,
yeah,
S.
S plus 2 all squared, right? So S plus S squared plus 4S plus 4. And now we just equate the coefficients. So we have 2 linear equations, F1 plus F2 plus 4 equals 4, and 3 plus F2 plus 3F1 equals 4. And we know that we can do this because we've already proven that the system is completely controllable. All right, so we quickly are able to get that both of them are F1 is 1/2 and F2 is -1/2. I've got a couple of other examples here, which I'm going to come back to actually at the end of lecture notes 20. I'm going to come back to those because I think maybe now, since we have a little bit of time, I'd like to introduce the concept of observer design and the structure of that. And then we'll return to the examples after that and on Thursday. Okay, so that. So are there any questions now about the process of designing this F, or the result that if the system is completely controllable, then you can always design an F, a feedback gain matrix F, to get those closed loop eigenvalues anywhere? All right, so the reason to do this observer design now is because the observer design process really mirrors the controller design process. Sort of like observability tests mirror controllability tests. And so let's sort of introduce what this all means. And it comes back to a point that I've said a few times. We're assuming that we can measure the state directly, and we can feed that back through the feedback gain matrix. So we've got this overall system. Here's our original system: x dot equals ax plus bu. Put an input. Coming out of that, I have a state x. And what I've been assuming is that I can take that state, feed it back through f, and let's do negative feedback like we've been doing, put in an auxiliary input v, and then I can go ahead and choose the coefficients of f to get the eigenvalues of this new system to be either anywhere I want, if it's controllable, or in the left half plane, if it's stabilizable. And that's just by looking at properties of A and B. But the problem is we typically can't measure the state. Right? We'd like to, but we can't. And maybe we wouldn't even like to, actually, because if the state is huge, that's a lot of wasted sensors, or potentially wasted sensors. What we do typically measure is the output. All right, so I'm gonna actually right now just have y is equal to cx. If I had d, I know that I could do everything that I'm going to do today. So I would have an additional block coming around, and I would just add it to y equals cx plus du. But for now, let's just assume that d is not there. Let's present the basic topology without d, because d doesn't really change anything. All right, so what I can really just measure is y. And what I have this great result that if I could measure x, I could do state feedback, but I can't measure x. So the question is, can I come up with an estimate of x using my output and my input? And perhaps if the system is observable, I can do that. And then what is the implication of using an estimate of x instead of x itself? Question?
I mean, so you said how we may not want to, or it may be very annoying to measure the state directly, so we can measure y instead, but wouldn't y also have just a lot of data as well? Or are you saying
but typically C, so typically when we look at a system, we have a lot of dynamics, and we're typically only measuring some subset of those. So C is typically a short, fat matrix.
Okay.
Okay, so the state vector is often inaccessible, and so what we'd like to be able to do then is to be able to come up with a device we'll call an observer, which takes the output. It also takes the input. Remember, for observability, the knowledge of the input and the output is important. And it gives me an estimate, which I'm going to call z hat of the state, where z hat of t is a vector in Rn, if x is a vector in Rn, which is an estimate of x. And then the question is, what do you do here? I'm just going to put a big question mark, how do you take that estimate and then possibly use it in controller design? So those are the pieces we have to look at. We have to look at what is this, and what is the connection between that estimate of the state and ultimately what you want to do, which is control the system. All right, so back in the, again, recent history, this is sort of 1960s. Okay, so that doesn't seem really recent to you, but it is recent in the scheme of math. There was a professor, he's still there, at Stanford, whose name is Lewin Berger, who basically invented this thing called the observer. So what we're presenting in class is called the Lewin Berger observer. Kalman was also, incidentally, at Stanford around this time, and they were all kind of working together. So there's kind of the Lewin Berger observer and the Kalman filter, and there are some similarities between them. But when we typically talk about deterministic systems and we talk about observer design, what we're presenting here is called the Lewin Berger observer. So David Lewin Berger is a professor. He's retired now, but he's in the management science and engineering department at Stanford. Okay, so consider the following topology. All right, so this is what is going to be the sort of putative observer that we fit in that box. At the heart of it is a little dynamic system. So you know the input to the system, and you know the output of this system. But you also know A, B, and C. So those are your knowns here. You don't know the state. So here, I'm just going to put a little system which is, I'll use Z hat, because that's my name for the estimate of the state. It's a little dynamic system which is called Z hat dot is equal to A times Z hat. All right, I know A. Okay, so I'm just going to form a new little dynamic system based on A. The output of that is Z hat. Okay. Actually, let's write it the way I have it in the notes to make it a little more clear related to the notes. So I actually separated the integration here. So I have an integrator. I'm feeding in the derivative of Z hat. I'm going to call that Z hat dot. And that integrates Z hat to get Z hat dot to get Z hat. And then I'm going to take Z hat and I'm going to feed back Z hat through the matrix A, which I know. And then I'm going to sum it with the following. So so I get Z hat dot is equal to A Z hat. So there you see what I had before, that little unit system. And I'm going to add to it a couple of things. I'm going to take the input from here. So here's my input channel coming in. And that input gets fed through B, which I know, B is part of my original model, and it gets into this equation here. So now Z hat dot is equal to A Z hat plus BU. Looks familiar, that's sort of copying my system. But there's another component coming in. And that component is, all right, I'm going to use a matrix T. I used a T for the similarity transform that we had in the previous lecture notes. This is not the same thing. So here, where T is it's an n by n out dimensional matrix. And just to say as a remark, not the same similarity transform T that we were using earlier. Not the same similarity transform T we used earlier. But I'll keep the same notation because that's what we have in the notes.
Is there a reason why we use T then?
No, I think I use T because probably Callie and DeSauer use T. Some people call it L for observer because it's L for Lewin Berger. I don't think Charlie DeSauer and David Lewin Berger really got along very well. I think there was some, I'm not sure, but yeah, there's some sort of referencing that doesn't seem to be kind of fair there. Oh shit, then this is on. Okay, so can you just delete that last one? Okay, it doesn't matter anymore. You know, hopefully David is not watching this. All right, so why would he be? He knows this material already. All right, so now let's just continue. So in addition to the Z hat dot is equal to A Z hat plus BU, we're going to add another little bit to the dynamics. We're going to take Z hat, which is, remember, it's our estimate of the state, and we're going to feed it through C to get y hat. Now that makes sense, right? Because if z hat were a good estimate of the state, and you feed it through the matrix C, which you know, then y hat should be a good estimate of the output. We're going to take y hat, so this is beginning to look a little bit like a nest here, but it's almost done, and feed that back here. And now the remaining thing that comes in is the actual output. So here's my output y, that comes from this channel, and that's fed in and it's compared with y hat. Okay, so this signal here is y minus y hat. It's an estimate of the error in the output. And that error is fed through a matrix T, which gets added to my new little dynamic system here. So if we write out the equations for what we've got z hat dot is equal to a z hat plus t times y minus c z hat plus b. So that's really just what we've written the block diagram for. Here's y minus y hat multiplied by t coming into this dynamic system. Okay, and actually now we can collect up the z hat, so that's actually a minus tc z hat plus ty, or plus bu plus t. Okay, where t is an n by n out matrix, not the same one we had before, and it's to be designed. Now you look at that and you're starting to say, aha, well, previously, earlier in today's lecture, we were talking about designing a matrix F to place the eigenvalues of A minus BF anywhere we wanted, if the system were controllable. So now, we're looking at this, we're not there yet, but we're saying, aha, well maybe that's quite similar to designing a matrix T such that I can place the eigenvalues of A minus TC anywhere I want if the system is observable. Yeah, okay, so that's kind of where we're heading here. But let's continue where we are with these equations. So we've got this system here, and now I'm taking this block here. You see I've got two inputs, the U and the Y channels, and what I'm feeding out is a Z hat. I could also feed out the Y hat, but what I've taken out here as my output is just this Z hat. So that's my output port. Okay, so this block now fits in that block here. Now let's take a look at what we've done when we look at those. Well, let's just look at the observer system for one more second. And let's ask, under what conditions is z hat a good estimate of x? All right, so a nice way to do that would be to look at the dynamics of z hat minus x, the error between the estimate of the state, or what we want to be a good estimate of the state, and what the state actually is. So let's look at z hat minus x. This is kind of my state estimate error. And what I know, I have an equation for x dot. So x dot is equal to ax plus bu. And I have an equation for z hat dot, which is here. It's a minus tc z hat plus bu plus ty. What is y? Y is equal to cx, right? Cx. So I'm just going to rewrite y as cx. And now I'm going to look at z hat dot minus x dot. So that's what I'm going to call the dynamics of the error, the state error, the state estimate error. Okay, so I'm just subtracting these two differential equations. So that's a minus tc z hat plus bu minus bu, so the bu's cancel out, plus tcx minus ax, which I can rewrite as a minus tc z hat minus x. right? So if I call this error E, then I've come up with an equation for the dynamics of the error between the estimate of the state and the state itself. And why is that amazing? I mean, this is why this Lewin Berger estimator is so cool. This is a dynamic system. Its evolution is completely dependent on the eigenvalues of A minus TC. So what if the eigenvalues of A minus TC were all in the left half plane? What would happen to E? They would all go to 0. I mean, isn't that amazing? It is amazing, right? Because if they all go to 0, they go to 0 independently of what's happening with your input. You know, you can just feed whatever input you want. You canceled, because you put it in here, you canceled out that effect. So you can have your input and your system kind of going crazy, but if A minus TC has eigenvalues in the left half plane, this error system will just happily converge to 0 with an exponential rate of decay, and your, after a little while, your z hat will basically look like your x. All right, so I kind of alluded to the fact that this is really very similar to the controller design problem that we just looked at earlier. Because if AC is controllable, we have kind of the dual of all the sort of steps we took earlier today in controller design. If AC is a completely controllable system, then there exists a matrix T such that those eigenvalues can be placed at any location you want them to be. It's the same problem we just looked at. And I can sort of show you, I mean, it's a very kind of neat thing to take a look at, but we could either prove it directly, or we could compare this problem with the proof that we presented earlier today. So let's look at this. Let's look at A minus TC. Okay, and let's look at it at this board over here so everyone can see. So just to review now, so we've got this error system. E dot is A minus TCE. Okay, and A is an n by n matrix. C is an n out by n dimensional matrix. And T is an n, it's going to be an n by n out dimensional matrix. We would like to place the eigenvalues of A minus TC using T, because T is our design parameter, in the open left half plane. Because then the error would converge to 0 exponentially. Okay, well let's so sort of compare this with what we did earlier in terms of A minus BF. So earlier when we were looking at the controller design problem, it's different, right? It's A minus BF. So here in this problem, the F was, it post-multiplied the B. In this problem, the T, the design parameter, pre-multiplies C. So previously A and B were given, and we have to choose F. Now A and C are given, and we have to choose T. Okay, but we have a nice result that the eigenvalues of A minus TC are the same as the eigenvalues, well, let's use the notation that we've always been using. So the eigenvalues of A minus TC are equal to the eigenvalues of A minus TC transpose. Right? If you take the transpose of a matrix, you don't change the eigenvalues. But that's the same as the eigenvalues of A transpose minus C transpose T transpose. Just bringing the transpose in. And now I have exactly the same problem that we solved earlier. Because I have my A minus BF. All right, so all the results that we have for that nice sort of therapeutic control design problem that we looked at earlier in today's lecture is the same as the nice therapeutic observer design problem that we're treating now. Where the only design, once you've got that Lewin Berger topology, the only design parameters you have are choosing the elements of this T matrix. Okay, so now the rest is just, let's sort of set it up and state everything, but now you have kind of the heart of controller design and observer design. So let's put it all together, right? So that's putting them together. We still have examples to do, we're not done yet, so we still come to class on Thursday. We're not done. And you have to do the course evaluations, because I want to get your feedback. But let's look at this a little more carefully. Let's put it all together. I'm going to erase the plane, and let's put those blocks together. So the observer in feedback configuration, page 6. So lecture notes 22, page 6. Okay, so I'll write this just a little bit more compactly. Here's the x dot equals ax plus bu. Here's x, it's going through c, we're going to ignore d for the time being, that's y. Input u is coming there. That input u is now also taken, and it's fed down to the observer. Okay, and so we can rewrite that, so that also goes through B. So I'll write out the observer since it's new to us, we'll write it out again. So it's coming in, here's my summation. And what comes, so I'm gonna, for convenience, I'm just gonna draw this a little bit backwards. So there's our z hat dot, that's fed through the integrator. What comes out of that is z hat, our estimate of the state. That gets fed back through A. We know all these parameters. Here's the feedback T, and T takes C z hat, so here's C z hat, which is our estimate of y, and it compares that with the actual y. Oh, oops, it doesn't go there, it goes through the summation. Let's just erase that, I'll put it through a summation instead. Right, so here. And what did we do? We did plus y minus y hat. That gets fed through this matrix to be designed. And what comes out is z hat. All right, so we've got, basically here's the equations of the system, x dot equals ax plus bu. And let's rewrite this again in terms of z hat. So z hat dot is equal to a minus tc z hat plus bu plus tcx. Okay, so what do we do? How do we link these together? Well, let's just sort of go with what we said over here. If we choose t such that the system, if the system's observable, we can choose t such that the dynamics of the error converge to 0 exponentially. So after a little while, z hat looks like x. So let's take advantage of that, and let's actually feed back z hat through the same matrix F that we would have used had we measured x to begin with. So F is just the same matrix F from earlier today, which was computed based on assumed knowledge of x. And then we're going to feed that back as if it were x. So this is f z hat, and that goes right back to u in the same way we had it before. So u is equal to minus f z hat. And I can put in a v here too, if I want. All right, so I just put that there, hoping that it would work. But let's actually take a look at those equations and see what happens. So now let's write out the equations for the closed loop system. All right, so x dot is equal to ax plus bu. but BU is BF Z hat minus BF Z hat. And then I've also got this BB here. And Z hat is going to be affected by that. So Z hat dot is going to be A minus TC Z hat plus BU, but U is now FZ hat plus V, right? So that's minus BFZ hat U is FZ hat plus BV. And then I've still got this plus TCX here. Alright, so now I've got these, this system. The overall system has an n-dimensional state vector here, and it's got an n-dimensional state vector here. So what was originally an n-dimensional system is now a 2n-dimensional system with if we think about like the whole state here, I can have like the first n components are x, and the second n components are z hat. Okay, so I can write out these equations, basically take these two sets of n-dimensional equations and write it out as one big 2n-dimensional system. So if I look at E, which is equal to, what did we say E was? Z hat minus x. Then E dot is equal to Z hat dot minus x dot. So we've already calculated this, right? So now we've got, we're still getting cancellation of BU. That hasn't changed. So it's still going to be the same as it was before, which is A minus TCE. Okay, so the addition of this auxiliary input V is not changing. So now, I guess instead of writing the state vector as xz hat, let's instead think about a bigger system whose state vector instead of xz hat is xe. Alright, so where E is equal to z hat minus x. Because that's a little more informative in terms of what I want to look at. I'm not so interested in what z hat is on its own. What I'm really interested in is the error between z hat and x. Alright, so now if I write out the big system, the dynamics of the big system, I have x dot and E dot. And what's that going to be? So x dot is equal to, so that's A minus BF times E. A minus, no, let's write that out carefully. So it's A minus BF. So instead of z hat, I can rewrite z hat as E plus x. And so this becomes A minus BF times x minus BF times E plus BD. Okay, and then, so what I have over here in terms of a state equation is, in terms of my new big state, is just this. So x